He has written and lectured widely on his book, The Mathematics of India, Concepts, Methods, Connections, was published in 2018, which grew out of research done at the Inter-University Center for Astronomy and Astrophysics, Pune, as the holder of a senior award of the Homi Bhabha Fellowships Council. I would like to invite our chairman, Mr. Shirsagar, to felicitate Dr. Divakaran. And now may I invite Dr. Divakaran to commence the lecture.
At least as an adult, someone who grew up in these gardens, in these galleries. I've been a visitor. I've known the museum very well for a very long time. So for me, it is a very, very great privilege, a very great pleasure to be here to address you. Now, there's still a problem? Yeah. Now, when I was trying to settle on a title for this talk, I debated with myself whether I'm going to keep the word mathematics in it or remove it. On reflection, I decided that I'll keep it because it will inoculate you. You will build up resistance, so it will not sound very bad. There will not be a great deal of mathematics in the talk. There will be some, but it will be mostly fairly straightforward, elementary, the kind of things we all remember from our childhood in our interactions with our mathematics teachers, often not very pleasant. So that is the background to this talk. Now, there are two parts to the title. The second part says culture. Culture is a very, very dangerous word. It's a very complicated word. I take it in the very broadest sense, which is that anything that we, as with our gifts as human beings, indulge in, our activities of every kind is part of culture for me. So mathematics definitely is culture from that point of view. It's a part of culture. It is price we have to pay partly for the specialization that we all practice in our daily lives, partly for the fact that the mathematicians themselves have made incredibly great progress in the last 500 years or so that it has become specialized, farther removed from the concerns of most people. So don't be upset, don't be put off by the title of my talk, okay? I'm going to begin my lecture. Now, the portrait of the person that you see on that title page is that of one of the greatest mathematicians not only India but the world has produced. His name is Aryabhatta. He's famous. Everybody knows his name. At least through the fact that we have many things named after him, including satellites and research institutions and all kinds of things. Aryabhatta was a very brilliant mathematician and astronomer. He lived in the second half of the 5th century and the first half of the 6th century. And we only know one book by him. It is called the Aryabhatiya, the work of Aryabhatta. And that was completed in 499 AD, when he was 23 years old. So this portrait, which is a modern, somebody's idea of what Aryabhatta must have looked like, is made by a person who normally makes Ganpati images for the festival. It was explained to him who he was, what he did, how old he was, what his personality was like, and I think he has produced an absolutely marvelous portrait. This is to be found. It's a full twice life-size standing sculpture of Aryabhatta. It's to be found whenever you go to Pune. Go to the Inter-University Center for Astronomy and Astrophysics and have a look and pay your tributes to this great man. His influence on the mathematical life of India, after he lived, of course, not before, was tremendous, very great. What I will be talking about is mostly what happened before him, because the seeds of what he did were all planted well before he was born. But that doesn't matter. The same spirit continued till the very end of mathematics in India, which is about 1680, when the European colonialism took hold in India. So that is the background. I'm going to start my lecture with, please ignore the fact that all the letters are standing sideways. The figure is the same, it doesn't matter which way you look at it. And the person who prepared the invitation card for this lecture understood this because he tilted it slightly. It doesn't make any difference. Now this is what I'm going to start with, this figure. What can I say about this figure? This figure, the first thing that strikes us is its visual. It's a very pretty picture, it's a very lovely piece of design, at least. But the symmetry of this figure should not hide the fact that it actually is a serious mathematical proposition in diagrammatic form. The question was, what it actually illustrates is how does one construct a square if you're given only a pair of compasses. And in this form, it is not in Euclid. It is not in the kind of geometry we learned in school. It is not in Euclid. It is in a set of texts called Shulba Sutra, which date from about 800 BC. The oldest of them is from about 800 BC. And the purpose, as I said, is to construct a square using only an implement to draw circles, which is a pair of compasses. I'll come to how to do that in a minute because that's important. What I've done is to use a regular ordinary compass. In the old days, of course, a pair of compasses was a string stretched tight between two pegs, because most of these figures were drawn on flat earth, on earth. This, as I said, is about 800 BC. That is 500 years before Euclid. Okay, this is among the very first manifestations of geometric imagination in our culture, and I will show later that it has a precedent, and that precedent goes back maybe another 1500 years. So that's part of what I'm going to say next. The real purpose of the Shulba Sutras was not to teach people geometry. Shulba Sutras are texts which are concerned with the design and construction of Vedic ritual altars, called Vedis in Sanskrit. And they form part of a body of appendices to the main Vedic text, the Samhitas, and these are called Vedangas. And this occurs not in any tract connected with mathematics or geometry or even astronomy, but comes in a tract connected with ritual. The construction of Vedis is part of the ritual. And this particular text is called the Kalpa Sutra. So as in every act of Vedic ritual, whether it is gestures or chanting or construction of making of bricks and using them to construct the Vedis, everything had to be done very accurately, very precisely. What can be more precise than the doing of mathematics? At least that we know. So what happened is that these geometrical constructions, which are described in detail in the text, is really part of the geometry of space, okay, and geometry of sacred space, because its purpose is sacred. Now, you notice that if you tilt your head sideways, you will see that one line is marked EW, east and west. Another line is marked N and S, north and south. And what that means is that The square, which is the result, the square is the dark line. Okay, A, B, C, D. There it is, A, B, C, D. So this square has to be aligned in the cardinal directions. Okay? And in Indian sacred literature, the direction east was the prime direction because that was the abode of the life-giving pre-dawn sun called Savitr in the Rig Veda. So the same Shulba Sutra text tells us a method of drawing the east-west line with great precision, independently of which part of the earth you are on, that is, of the latitude, independently of the season, because you know that the direction in which the sun rises depends on the season and depends on the latitude. So the true east-west is drawn without reference to such potential disturbing factors. And so what we have here is abstract geometry in confluence with very highly non-abstract building of the structures with bricks, and at the same time a mystical allusion to the power of the life-giving sun. So this is very typical of a lot of Indian geometry in the beginning. So we have brought these many disciplines, many concerns, the human concerns together. There are other geometric theorems in the Shilpa Sutra, some of which are of a high degree of mathematical sophistication. All of them straddling the ground between the intellectual and the sacred. So geometry was not mathematics. Geometry was also a sacred act. Doing geometry was part of the faith people had and their belief in its power to influence the natural phenomena. So that is true of many other things, and one of them is something which we have all heard the name of. It is called the theorem of Pythagoras, which says something, it doesn't matter what it says in general. But Pythagoras lived 250 years or 300 years after the things that I've described, I'm going to describe also now, happened. Now, the moment of truth. Again sideways. If you take a square, the theorem of Pythagoras says, the special case, says that the area of the square you make on the diagonal of a square, diagonal is the one which joins the two opposite corners, is exactly twice the area of a square you can make on the side. That's one of the few mathematical things that I'm going to say. It's very straightforward. It says, take a square, draw a diagonal, make a square on the diagonal. Its area is twice that of the area that you will make on each side. Now, in this form, this is not the form in which you learned in school. This is a special case. But in this form, you can see it is pretty obvious. You don't have to prove anything. The statement of the theorem and its proof are in these diagrams. For example, if you take the first one there, this is my square, original square. This is the diagonal. This is the square on the diagonal. And this is the square on the side. Now, the little square inside, which is the square on the side, has 4 equal triangles, and the big square, which is the square on the diagonal, has 8 equal triangles. So, the truth of this mathematical statement is pretty obvious. You don't have to be a mathematician to see this. You only have to have a good eye. In fact, the very great mathematician, astronomer from Kerala, who lived in the 15th and 16th centuries, says at one point that this is called the theorem of the diagonal in the Indian mathematical literature. It is not called Pythagoras' theorem, for the obvious reason that they didn't know about Pythagoras. And he says, Nilakantha, his name is Nilakantha, he says that this particular result is self-evident to the intelligent. You don't have to be a mathematician. So geometry began in this way. Geometry didn't begin. In fact, I'm going to take you back a little bit. If you go back, the story of the square doesn't begin with the Shilpa Sutras. I take you back another millennium and a half to the beginnings of the sophisticated urban phase of the Harappan or Indus Valley civilization. See, the Shilpa Sutra is 800 AD, let's say. The mature phase of the Harappan civilization is maybe 2500, 2600 BC. So almost 2 millennia earlier. And when the excavations were made in the 1920s, beginning in the 20s, and all kinds of wonderful artifacts were turned up, one of the things they found is it's a jar. It's a painted jar. It had to happen. Yeah, it's a painted jar. What I want you to concentrate is this band, the band in the middle. There. This band. Okay? Keep that in your mind, and we go back to this figure. You see this four-petaled rosette, which came about as an intermediate step when I was trying to make a square with circles. They are the same. They are the same design, same pattern. In fact, I can make a square if I like. I can make a series of squares like this. That's one square. Perfect, exactly the same thing. And with the eye attuned to the original first square that I showed, it's pretty obvious that there must be a connection between these two things, because it is not every day that you come across fairly complicated designs, especially in the early, when you didn't have computers generating millions and millions of design from a few elements. I mean, these were things people had to imagine, conceive, draw properly, and recognize for, oh, come on. For what they are. Now, one would imagine that the purpose of this, decorating a jar, is not necessarily sacred. It had nothing to do with the mystical, mythical, magical Vedis of the Vedic people. It's purely decorative. We can see no reason why it should not be decorative. That is to say, there is nothing that goes with it which shows us that there is an element of the sacred. So it's very, very, very tempting to think that, you know, when the Indus Valley civilization disappeared, the mature Harappan phase disappeared, about 1800, 1900 BC, there are many theories about what happened to them, but of course nobody runs away to, many people probably travel to other parts of India and perhaps even to other parts of the world like Afghanistan. In particular, there is a strong theory which says that some of them actually traveled to South India and became, in course of time, the founders of the Dravidian culture. Okay, independent of all that, there will be people who stay behind. They will have a collective memory of what it is that they were doing before they became impoverished, before they lost their civilization. If that is the case, it's very easy to understand that they will have the skills to remember how they constructed these decorative patterns by using circles which intersect with one another. And not only that, that they will also remember, if they had already done it, how the direction east was determined, or the direction east-west was determined. Now everybody knows that the Indus Valley civilization has many, many other artifacts, and among them, one of the things that people are struck by is the fact that the streets, the grid of streets, the Indus Valley people, before that, I'll show you another, exactly the same thing. Yeah, you can see the same pattern there. There. This is the same pattern replicated sideways. That's how it is made. So the conclusion I would like to draw is that there was continuity between, civilizations don't disappear. They don't just vanish into thin air. They leave behind remnants which the succeeding civilizations often take up and build up into new ways of looking at the world, new ways of implementing ideas which are buried in some particular elementary form in the earlier civilizations. And I think that's what happened. That the culture of making these patterns, decorative patterns, began in the Indus Valley, continued into several hundred years later, or more than 1,000 years later, into the Vedic civilization, where it became sacred. There are other examples of similar things. Like, for example, anyone who has seen any photograph, any picture of the Indus ruins of Indus cities will remember, the first thing that you remember is not any of these small details, but the millions of bricks that you see everywhere. Every Indian Indus Valley site has large numbers of bricks, and most of them have. When that happens, you ask yourself, what happened to this culture? Because making bricks is not a trivial thing to do. Making bricks requires high technology at that time. You have to fire clay at a certain temperature, and you have to mold them, you have to do various things, and the molding must be done carefully so that everything is rectangular. The Vedic people didn't have bricks except in one context. The context in which baked bricks were used in the Vedic civilization was precisely the construction of the same Vedis, to make them with bricks. To make them with bricks cut and measured precisely, because Vedic ritual required precision. So, give me a minute, huh? So, the geometric themes which we see continuing into future time in very slow but very definitive ways is possibly a link between what happened before, what happened later. And these links are not, as people often say, oh, there is a link between the Vedic and the Indus civilization. It's what is the word used? Ideological, that is to say, in their beliefs, in their various other things, like the notions that you have of space and so on and so forth. But that is not the only story. You actually have abstract but artifactual elements which continue. Abstract because it is geometric, artifactual because you can actually see them. Excuse me. Now, how did they make, there's these Manhattan-like street grids in Indus Valley ruins. How did they make them? I say the same thing, the principle is the same, because if you make a series of circles in the same way as the earlier one, maybe I should explain very briefly how that is done. Yeah. What you do is, that is something which works better. Yeah. What you do is, you draw the east-west line, because there is a method for that described in the Shulva Sutras, which probably is what the Indus Valley people also did many 100 years earlier. You draw this east-west line, then you take a compass and draw a circle, this one, the one which passes through N dash and S dash. That is a circle with this as center. We do the same thing here. They'll meet at N dash and S dash, join the 2 points, you get a line, and that is the midpoint of this line, EW. Then with that as the center, you draw another circle, this one. Okay? Then you get, in that way, you get what? You get the point N, S, E, W. You make circles with N as the center, that is this circle. E as the center, that is this circle. Just find out where they meet. That's the square. Okay. This uses a principle, it's a very elementary principle of geometry, which says that when I have two circles cutting one another, one circle, another circle, the line joining the 2 points where they meet is perpendicular to the line joining the two centers of the circle. That's actually what we use. It's a very elementary principle. It is in Indian geometry, it precedes, this theorem precedes the theorem of Pythagoras. It's already known to the Indus Valley people. There used to be a belief that the Indus Valley people actually determined the east-west direction by looking at the pole star. That's not a very sensible suggestion because you see the pole star only when it is night, and I don't imagine they had LED lights in those days, so how would they actually mark things on the floor unless they took a lot of trouble to illuminate the place very closely. And the pole star also is not really very fixed. You know, it moves. It's subject to various kinds of motions. So much more natural is this method. You don't determine the north direction, you determine the east direction using the sun, which is done during the day. So the Indus Valley people had a tremendous sense of geometry and symmetry. I mean, first of all, they were very fond of, they were attached to the idea of perpendicularity, you know, like bricks with perfectly shaped rectangular faces. Then weights which are perfect cubes, almost perfect cubes, doubling in volume or weight in every step. And that, for the mathematically oriented people, is a rather interesting problem because to double the volume of a cube, you have to determine the cube root of 2. And that is a problem which is not easy to do. And this is a problem which figures in another civilization, in another geography, in the famous story of the Oracle of Delphi, who, in order to avoid an attack of plague on Delos, told people, find a way of doubling the cube. You cannot double the cube very easily. So there is, these little mathematical problems give us a window into the material culture of the times, in addition to their purely geometric culture. Now, if you were to conclude from all this that the origin of geometry in India is secular, it's non-faith related. It began with the Indus Valley, in the Indus Valley, as a design tool. It got sanctified in the Vedic times. The Vedic people sanctified everything. They sanctified the bricks, which the Indus Valley people used in a purely materialistic, for a purely materialistic purpose, to make buildings. They got sanctified because they were used only in the sacred structures. But the great French scholar of the Vedas, early India in general, Louis Renou, in one article which is called the Vedic House, the Maison Vedique, he says, the great mystery remains. He said, you know, the Aryans, the Vedic people, constructed their houses of perishable organic material like grass, wood, wattle, cane, bamboo, and they all disappeared. Except they made their Vedis with durable bricks. And it's a curious fact that certain tribes in northwest India, this was written in 1930s, you know, when the consciousness of the Indus civilization was still very rudimentary. And he said certain tribes in northwest India actually made large numbers of solid structures with a much higher technology, which is that of baked bricks. So the So technology tend to be worshipped. We do it even today. Except that it is a digital technology we worship these days. Technology tends to get worshipped. The first fire, the use of fire for civilizational advancement in various ways, it became very quickly a matter of being divine, being divinely inspired. Same thing happened with bricks. The same thing happened with geometry. Same thing happened with various other things, but we will not talk about it now. Now, later, geometry took two paths in India. One of them is associated with the great Aryabhatta, whose picture you saw earlier. And what does it say? What did that do? Aryabhatta invented a discipline, mathematical discipline, geometrical discipline, which is called trigonometry now. You may remember, some of you may remember this from school days. This was very practical, very useful. You couldn't do astronomy without it. But there was another branch which did various developments of geometrical things which had no practical applications at all. They did it for the beauty of the thing, and they were as beautiful, but in a very different way from the pictures that I drew here, that I showed here. They were beautiful from an abstract point of view, and that beauty can be appreciated only by well-trained people. It is the difference between a good film song and a great classical piece of music. That is to say, it's not for everybody, it's for people who are properly tuned. But these people, even when they were moving away from the practical, the applicable notions of mathematics, they were very aware of the societies in which they lived. They knew where they were, why they were there, what was happening around them, and how their own views are affected by such things. For example, Aryabhatta, he says at one time, he talks about time, and he says time is anadyanta, it is without beginning, without end. What gives it a structure? What makes it appear to be periodic, that things repeating themselves over and over again, is the motion of the planets. And one such long period of time in which all the motions repeat their motions, all the planets repeat their motions, is what he called a yuga. Now, this notion of time is not something which came out of the blue. This notion of time is precisely the notion that the Mahayana Buddhists had of time. Time for them was infinitely extended, but having a periodic structure. Things repeat themselves. In fact, the world itself repeats. The world repeats itself over and over again, both in time and in space. And Mahayana Buddhism was its very pinnacle at the time, just before Aryabhatta lived in northwest India. And what happened at that time was that this picture became so popular, so widely accepted, that the Buddhists had to invent entirely new a sacred order of beings in order to account for their power over this infinitely replicated universes. And that is how the form of the Buddha called Amitabha came into being, in which is a lot of all the worlds repeated in space and in time. And his various subordinate people, the Bodhisattvas, looked after each of them, some of them a little more complicated way. So there is a very strong interface between faith and geometry, but in a very different way. Not as it was in the Vedic times, but in a different way. Well, there are other things like this. For example, Aryabhatta describes the Meru mountain, the axis mundi, the axis which connects the earth to the upper world, the world of the gods. That is the Meru mountain, and around the Meru mountain, Aryabhatta is not given to poetic excesses. He's a very, very down-to-earth, very practical sort of person. And he says, he gives a description of the great visual garden which surrounded the Meru mountain, and that is identical. That description is identical with the description of the Buddhists of a place which they call Sukhavati, the land of bliss. So The Indian writers, especially on intellectual subjects, they did not spend too much time on peripheral subjects. One exception to this is Bhaskaracharya, the great mathematician and astronomer who lived in the 12th century. Apart from that, most of them are very businesslike. They say what they want to say, and then they say goodbye. That's it. And at the end, they will give, if they are in a good mood, they'll give 2 lines in praise of their particular god. That's it. No more. So, there we are. So geometry is a mathematical theme, so I'm happy to be able to get through a fair amount of geometry without actually involving too many complicated things. Now, of course, mathematics, people say 2 main branches. One is geometry, the study of space. Space has become sacred. It has lost its sacredness. It has become very mundane again. The other is numbers. The numbers were sacred in the Vedas. There are many numbers which we consider to be auspicious even today. But we don't know very much about the number system that the Indus Valley people used. So I can't say very much about it. But the Vedic people thought of it that way. I'm not going to look at it today from that point of view. I'm going to look at numbers from the point of view of its connection with language and grammar. Okay, now this is a fairly tricky thing. See, the ocean of mathematics, Aryabhata says that in one of his few lapses into poetry, in real, literary flourish, he says that the ocean of knowledge has many uttamaratna, many best of gems, the very finest gems. And it is by the boat of one's own intelligence that one brings to the surface the best of them. That is to say, forget about divine inspiration, forget about all the other things that people talk about. Because, Aryabhata also lived at a time when the Puranic culture was being initiated in many parts of India, many parts of North India. And from the point of view of Puranic, the great Puranas are wonderful as fiction. Wonderful stories, and most of them are not to be interpreted literally because they won't stand a literal interpretation. If you read them as creations of the mind or the imaginations of people who were out to prove, let's say, that Mahadev was the greatest of gods or Mahavishnu was the greatest of gods. If you think of them in that way, it is great work. But if you want to try and extract from the Puranic literature things about the life of reason, the life of the mind, then that is not a good place to begin. And there are places in which Aryabhata's followers, after describing the astronomical phenomena such as the eclipses, in terms that we understand today, that is to say, as a result of the play of the shadow of the 3 bodies, the earth, sun and the moon, will then say, but there was this great astronomer, great mathematician called Brahmagupta, who says the eclipses are causing. Brahmagupta was a tremendously good mathematician, but he was very backward in his view of the universe. So if he says that it is caused by Rahu and Ketu's following planets, following our sun and the moon, that is Pauranika Shruti, that is a hearsay, Puranic hearsay, that is hearsay from the Puranas. Do not pay attention to it. So there is this constant tussle between the mathematical practitioners, among the mathematical practitioners, between the rational view of the world and a faith-based view of the world, in which orthodoxy was its own reward. That's enough. You don't have to worry about whether it makes sense in other terms. Now, the urge to count is very primitive. We want to know how many of this, how many of that do we have. And there are very, very beautiful passages, very striking passages from some of the Vedic literature in which you can see the struggle it has been to come to a resolution of this particular problem. It has not always been easy going. For example, well, we don't have the time. I'll later. So we need a measure. What is counting? So how do we do it? We do it by counting. How do we count? We count by saying 1, 2, 3, 4, 5, up to 10, and so on, and so on, and 10 to the power 14, that is 1 followed by 14 zeros. These are numbers which occur very freely in India. Okay? And go on as long as we can. We do it routinely, we do it effortlessly, but we also know that this way of counting using 10 as the unit, 10 is like a meter stick, I want to measure distances, I will take a meter stick and go with it. If I want to measure numbers, I'll take 10 as my meter stick. Measure how many tens will go into this. For example, in 2019, how many tens are there? How many, after that, what do you do? And so on and so forth. Now, the first evidence of everybody knows that this decimal way of counting came from India. What everybody doesn't know, what most people don't know, is that its earliest phase actually coincides with the beginning of the Vedic literature, in particular the Rig Veda. There are two of the early Vedic texts which are very, very, very rich in number lore, in the way in which we can understand the origins of this number system. One is the Rig Veda, which I will come to in a minute. The other is a version of the Yajur Veda called the Taittiriya Samhita, or sometimes called the Black Yajur Veda, or Krishna Yajur Veda. So these texts have full of numbers of various kinds. And the analysis of the way these numbers are formed in these texts is proof that the decimal number system was perfectly well understood at the time the Rig Veda was written. Now, to understand this, we have to do some things. This is connected with language and grammar. And that is so because the Vedic people had no writing. This is now generally accepted, even though some people still doubt it. There's plenty of evidence that there was no writing during the Vedic times. Whether this absence of writing was caused as a matter of choice, that is to say, we decide that what we learn, the Vedic people considered the word Vach as a goddess. Okay, Vedic people considered every meter, such as Gayatri or Anushtup or Arya or Trishtup, every one of them was considered holy. Everything was holy to the Vedic people, especially things which fitted in very well with their worldview. Their worldview is that the spoken word is the ultimate way in which we communicate. There is no other way, especially the way in which we communicate with the gods. So, the structure of decimal counting is to be understood from the way. So if you don't have writing, how do you write 2019? I have no symbols. I have nothing to write down to represent these numbers. So what I do is I give them names. So for example, 1 is Eka, 2 is Dvi, and so on, 9 is Nava, and so on and so forth. And then that's not enough. When you come to 10, since you're using 10 as the base, 10 as the stick with which to measure numbers, I must have a name for 10. I must have a name for 10, Dasha. Then I must have a name for 10 tens, which is Shata, 100, and so on. And the Rig Veda, such numbers go up to 10,000, which is called Ayuta. However, the Taittiriya Samhita goes up to 10 power 19, that one followed by 19 zeros. And because these we now replaced symbols by numbers, when we combine numbers to form something like 2019, I have to combine words. When I combine words, I have to use grammatical rules. Grammatical rules are not constructed, not created just to deal with numbers. They're constructed to deal with language as a whole. Therefore, the number names must conform to rules which were made for Vedic Sanskrit as a whole. And this is very, very rich source of information on the mechanics of constructing these number names. When that is done, we discover that the Vedic people had total mastery of the decimal number system, complete. Every single number that occurs there, some of them are very complicated, like for example, 3099, 3,339, that occurs. Then 60,099, that occurs. And the names are there. I mean, I can quote the names to you. And they actually tell you very clearly that the grammatical rules made for adding two numbers or grammatical rules made for multiplying two numbers are different. They're not easy to analyze. They are quite difficult. But when you've done the work, you know. They are unambiguous. They are completely clear. So there is a misunderstanding in the historical circles that Indian decimal number system dates from about 300 AD. And the reason why that is said is that by no stretch of the imagination can we take the first occurrence of dated numbers written beyond that date. So they say, all right, Indian decimal number system began in about 300 AD. But if you have the system depends on a certain principle. That is, how do you use 10 as the unit by which to measure big numbers? And that can be expressed in many different ways. One of them is by writing symbols. The other is by giving them names and combining the names together. And when that is done, the date of the origin of the completely perfected decimal number system goes back to at least the time of the Rig Veda, because in the Rig Veda, which is about 1100, 1200 AD BC, in the Rig Veda, it is already there. It is already there in completely unambiguous terms. I mean, the Rig Veda, who would have thought of the Rig Veda as the source for the history of mathematics? The Rig Veda has about 2,000 number names in it. And when you look at them, which we have done, collaborated, there are only 5 examples we found there was some ambiguity out of 2,000, close to 2,000. Everybody else, everything else fits in perfectly well with the grammatical rules, and I can tell you that this is exactly what this number is. I mean, this is not such a trivial thing. For example, I looked at Aryabhata earlier. The Aryabhatiya has 108 operative verses. So it is known in many circles at that time as Arya Ashtashata. Ashtashata meaning 108. 19th century scholars who had not seen the original Aryabhatiya, had only heard about it from other people's writings, translated Ashtashata as 800. 800, so it must be 800. Actually, there are very clear rules, even in Panini, which tells you that that analysis is wrong. Correct analysis tells you that Ashtashata can only mean 108. Then if you want to say 800, you have to say it in a different way. So it's a complicated thing. But at the end of it all, it is the intermingling of language, what I call the grammar of numbers and the grammar of language, which has produced for us this insight that this is what the decimal number system was. It was created well before 1200 AD because it takes time to perfect such things. And therefore, it's very clear the grammarians benefited from this as well as the mathematicians benefited from the grammar. Yeah. So, I forgot to say this. Please excuse me, I should have shown this. I like this slide, the refinement and power of the Indus Valley sculptors is terrific. The Indus Valley people were very, very powerfully influenced by the notion of symmetry, geometric symmetry. And, there are about 450 independent characters in their language, in the script. And about 70% of them have a symmetry between the left and the right, the mirror symmetry. That is to say, you draw a line through the middle, the two sides are the same. Look at this. This is the writing on top of this. This is symmetric, this is symmetric, this is symmetric, this is symmetric. This is not quite because of this. This is not, this is not, and this is. Most of the letters have this left, right, or mirror or reflection symmetry. So that's just something I should have said earlier. This is not very important. This illustrates a question. You should have asked me. I forgot to say that I quite like it when people interrupt me in the middle, ask questions before I get on to something else. One of the questions I expected is, it's all very nice to talk about numbers, but where in all this is the zero? Shunya, India's vaunted gift to mathematics, if not to all civilization. Where is the zero? Everybody says the great contribution of India to numbers, mathematics of numbers, is the use of the zero. Where is it? Now the fact is that if you are burdened with the need to find names for things rather than symbols for things, as I've been trying to say is what happened, then you don't need a zero. Because for several reasons. One is that I already know where do you need the zero? If I want to write 100, I have to say 1, 0, 0. But if I want to say 100 or shata in Sanskrit, where is the zero? I don't need a zero. I have a name for the whole thing. Okay. If I want to write 2019, I have to write a zero in the middle, 2019. If I want to say 2019, I don't need a zero. Then the other thing is zero is a number standing by itself for nothing at all. When you speak, when you use words, you don't need that zero, because nobody will say that there are zero supermen, let's say, because this is the age of supermen. What people will say is there are no supermen. The language does the work that the number zero is supposed to do. I simply say, I have no belief in God, let's say. I will not say I have zero belief in God. I will say I have no belief in God. So for that reason, in an oral system in which there are no symbols to be written down, there is no need for a zero in the numbers. You can count perfectly well without zero. You can even do arithmetic without zero. It's very easy. It's not difficult at all. Okay. So what happened to the zero? This is the reason why the zero actually appears on the Indian scene very late. Even though the basic idea of numbers and how to measure them by using 10 as a meter stick is very old, goes back to the Rig Veda. The actual written zero appears first in India on this little scrap. This is a folio from a thing which was very much in the news about 2 years ago, called the Bakshali manuscript. This is something which is kept in the Bodleian Library in Oxford, and this manuscript first used a symbol for zero. It's a written manuscript. The mathematics is written down. The numbers, there are symbols for numbers. Okay, this is the first manuscript that survived, and the symbol they used for it was a dot. You can see there are lots of dots on that thing. They're not all zero. Quite a few of them are. Some of them are dots which come in writing letters, but several of them are zeros. The dots served other purposes in this manuscript. So I say this because this was dated 2 years ago. The story of this manuscript is very romantic. This is not the time for it, but it actually is very fascinating. It ended up in Oxford around 1920. And for a long time, nobody dared to date it in any scientific way. Finally, 2 years back, somebody did. And they found 3 different dates for 3 different samples. One around 300, one around 600, one around 900. Now, the reason why these dates are so variable, the reasons are not known. We don't know why. We don't know why they differ so much. But we do know one of them is 300. And that is a perfectly reasonable date to have for the zero, because It is around that by 300 AD, writing had come to India 600 years earlier, because writing came to India first in the inscriptions of Ashoka, 3rd century BC. By 300 AD, Brahmi writing was everywhere, all over India, on coins, on rocks, on temples, all kinds of places. So the first zero symbol occurs pretty much with the advent of writing in India. So I'd say something. What does it say? It says that now you cannot do without a zero, just as you cannot do without a zero when you write 2019 for 2019. Much more interesting than the idea of zero is the idea of infinity. Now, infinity is a word used in many, many different ways. I mean, in this context, it stands for the fact that it is shorthand for the fact that there is no end to numbers. You can keep on counting. I ask you, somebody give me a very big number, I'll produce a bigger number, add 1 to it, or multiply it by 10 in the Indian way of doing things. So, this was an idea which intrigued the people from the earliest times. I told you the Taittiriya Samhita has numbers, names for numbers, which are as big as 1 followed by 19 zeros. In the following 1,000 years, the fascination never ended. People kept on writing bigger and bigger lists. And they gave these powers of 10, the 1 followed by many zeros. They gave them names, and they made long lists of names, and they made some mistakes, because who can remember so many names? So, the idea was in the air, but nobody knew what to do to tame the idea of infinity. It was actually tamed. The perfectly logical way of handling infinity was finally discovered by, I'm saying this for a special reason, by a man, a very, very great mathematician from Kerala, one of the greatest anywhere, at any time. And his name was Madhava. A name even people interested in the history of mathematics have not heard of. I mean, not too many have heard of. And he did it in the course of inventing a discipline called calculus, a fact also which many people have not heard of. Now, part of my activity as an aspiring historian of mathematics is to bring justice to Madhava. It is happening. I'm very happy. More and more people now realize that this guy was a very great man. Nobody knows about him. Now, the struggle with infinity began a long time back, not just more recent. One hopes that if you count long enough, you will come to the end. No, one doesn't. There is no end to it. And it took a long time to dawn on people that there is no end to it. And even when they knew there was no end to it, it took even longer to know what to do with this damn thing. What do we do? The thing doesn't end. And it went on, and this is the problem which Madhava sorted out in a very, very logically satisfactory way. The name for the number, 1 followed by another 5 minutes I can take, was Loka. Loka is the whole world. They hoped that they have come to the end of the numbers. Well, of course they did. And so what happened was that they made many different patterns of numbers, and they always said that, this is followed by, they will count 1, 2, 3, 4, up to 100, and they will almost offer oblations to these numbers. Numbers were sacred. And then they will say, I offer an oblation to all, sarva. And example? It says, hail 4, hail 8, hail 12, hail this thing, then finally hail 100, then it says hail all. Chaturbhya swaha, ashtabhya swaha, Shataya Swaha, Sarvasmai Swaha. And there are 9 such sequences in the Taittiriya Samhita. Each of them go up to 100, and each of them ends by saying Sarvasmai Swaha. That they knew that you can count forever, you'll never come to the end of it. Okay. That is thing. I mean, this caused a great deal of thought. Now, the particular episode connected with the infinity had a linguistic counterpart. Grammatical expressions are not also without end. I mean, you can go on forever, and you can make new words, new expressions. So it is unending. And that was recognized also very early, that the nature of infinity is independent of numbers. It is a phenomenon which concerns language in particular, was recognized very early, but the linguists also had a solution to this problem. Solution was, if you will excuse my being slightly technical for a minute, that rather than count things one by one, enumerate them, you say all of these objects together form one class of objects, and I will write my rules down so that it will apply to every member of that class of objects. I don't have to enumerate. For example, I will say that the class of all even numbers, 2, 4, etc., 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 have the property that it can be divided by 2 without leaving a remainder. I don't have to say 2 can be divided by 2, 4 can be divided by 2, 8 can be divided by 2. Somebody will say, what about 102? Can it be divided by 2? So you don't have to enumerate. Now there is this absolutely magnificent little story, a little fable from this particular way of solving the problem of infinity is due to a grammarian, the greatest grammarian of all time, anywhere, Panini. Okay? And Panini had a commentator called Patanjali, not the Yoga Sutra Patanjali, another Patanjali, a grammarian, probably not the same, who knows. And what Panini said was that classify all words into a certain finite number of classes, like nouns, like verbs, like affixes, prefixes, suffixes, and so on and so forth, and find their subcategories. That is to say, let's say, masculine gender, singular nouns in the nominative case. One grammatical characterization. For all such things, this is the rule that you follow. Then I don't have to list all masculine gender, singular number, nouns in the nominative case. I don't have to do it. I apply it to all. So this is principle of categorization, or Panini called it a metalinguistic principle. I mean, modern scholars call it a metalinguistic principle. A principle which goes beyond linguistics, actually involves logic, or more accurately, set theory in modern mathematical language. So the grammar and numbers, the interaction never stopped. Now the fable is wonderful. I like it very much. Brihaspati was the preceptor of the gods, and Brihaspati was trying to teach Indra, who was not famous for his intelligence, for his mental acuity, grammatical expressions. And he was doing it one by one so that Indra could follow him. At the end of 1,000 years of the gods, which is a very large period, very long period of time, they got nowhere. Okay. So, Patanjali says, it was clear that rules are required. Rules which are both general and particular. What is the general rule? Then the general rule is, what he says is that there must be a work which describes general rules and particular rules. The work which describes both this kind of rules is Ashtadhyayi, Panini's great grammatical text, which tells you, for example, this classification principle or the categorization principle. That is a general rule. It applies to everything. Particular rules is like, for example, if you make a sandhi between two vowels, A and E or A and A and U, one goes to A and the other goes to O. That is a particular rule. So this give and take between between linguistic constructions, notion of infinity. This has been going on for a long time and is still not completely dead, because Paninian methods are apparently now being re-examined very closely by certain computer theorists because they're very useful, apparently. I don't know. So the numbers have to be given names. That causes a lot of problems because, and it caused a particular set of serious problems for another very great linguist called Bhartruhari, who lived probably at the same time as Aryabhatta. And in his way of looking at things, things have to have a name before they can exist. Okay. How do we say an abstract thing? Like, when I say fiveness, the quality of being five in number, what is it? It acquires a meaning only when I give a name to the number 5. So this is, now this is a principle for which, linguists are very good at giving names. Whenever they find a principle which works in a certain way, they give it a name. Like, for example, Bhartruhari's major preoccupation was the cognition of language. How do we express our ideas in language? And how do we, when we hear that language, how do we convert them back into ideas in our head? That was his main thing. And for that, the modern linguists have a very good name. They call it the Spota theory. Spota is a word used by Bhartruhari. Then, but they have no name for Bhartruhari's principle that things don't exist. Things cannot be unless they have a name. So in a light-headed moment, I suggested the name, very learned-sounding name, what is it? Ontological nominalism. Does anybody know what it means? And I said it in some lecture, and the people liked it very much. So now I remove the ontological. I simply refers to as nominalism. That is, the existence, it cannot be before it has a name. That is the general principle. You have to make it tangible. You have to make it tangible by giving it a name. This is another example of the fact that oralism, that is to say, the idea that things must be spoken, uttered, before they acquire meaning, it became very, very powerful in India. It still has a big hold in India. So to name, you have to know. To know, you have to name. The other way. The funny thing is, this is a very powerful meta-mathematical principle. It is not just a meta-linguistic principle. Of course, it makes the classification, the categorization which Panini used. It's a very powerful, it's really modern set theory in its elementary form. The Indian mathematicians had nothing to do with it. Nobody knows why. Nothing. Great, great puzzle. Grammarians were ahead, and people who say that in India the first science was and will always be grammar, I think are not wrong. Okay, so to rush now. I will end my talk. Yeah, but I have to show one slide, from a very late time. These are not just. This is what Bhartruhari says about. He knew mathematics very well. This is his analogy of how notions from numbers can be used in grammar. Okay, I leave it there. So, subsequently, this was very popular with mathematicians, this principle. Things must have a name. Indian mathematical texts have no equations, no symbols, no nothing, except for that one thing that I showed, the Bakshali manuscript. Nothing else. And till the very end, till 1600, texts written have no equations, no symbols. And that is a measure of the influence Bhartruhari had on the doing of mathematics. For example, this great man, the man who is the author of what I call the first textbook of calculus, who described Madhava's work, look at the things in boldface. He said, there is no end to the names of numbers. Hence, we cannot know all the numbers themselves and their order. That is to say, first comes the name, then comes the thing of which it is the name. So that's the kind of influence he had. But of course, if everybody had stuck to this principle, Madhava would not have been able to invent calculus, which he did. Therefore, you say these things, and you do what has to be done. What has to be done is to imagine the numbers which don't have a name. Any long list of numbers will be, from a certain point onwards, it will be nameless. And last 2 minutes to 3 minutes, I want to go back to a very general issue which cuts across all of mathematics, not just geometry or numbers or this and that and so on and so forth. The issue is, how can we know whether what is claimed to be a mathematical truth, say the theorem of Pythagoras, is in fact true? In other words, what is a proof? Now, most people use the word, mathematicians have a very precise meaning for it. The ordinary people use it in very loose terms. So the question really is, when I say what is a proof in an infallible sense, in a sense in which it is exactly known that this is true, this is not true. Now, this is a problem which many cultures have struggled with, the Greeks and the Indians in particular. And in India, they started worrying about it a very long time back, and they're still worrying. I mean, in fact, modern mathematicians still discuss the question of how do we know that a certain statement is true or not true. One particular classical Greek technique of deciding whether something is true or not is called the principle of the excluded middle, or the rule of the excluded middle. It simply says that every statement must be either true or false. That is, there is no middle ground. Okay? Every statement must be either true or false. It may be obvious to most of us, and I think most people will accept that it is obvious, but wait a minute. So the way in which it is used in mathematics is to say that if I want to prove that something is true, I begin with the assumption that it is false, it is not true. If I want to prove that the earth is spherical, I begin with the assumption that the earth is flat, for example. Okay, it's a very bad example, but for the time being, we'll do it. Then you show that the assumption I have made will lead either to a contradiction or to an absurdity. Okay? So it's called the law of the excluded middle, but this is the kind of argument we use all the time in our daily lives. For example, it's very useful when you want to be nasty, for example. I give you an example. To make sense of our public life, we often use arguments like, Mr. X is dishonest. Why? Because if he were honest, the opposite, the negation of the thing I want to prove, then he would have remained poor, at least not so rich as he is now, which is a contradiction, because he is very rich. Okay? So I call this the ABM principle, assets beyond means principle. Okay? And this is something we use all the time. But the Indian logicians never accepted this. They said that this is not obvious to us, and there are very good reasons why they didn't believe it. But historically speaking, this also has a connection with philosophy and with religion, because the Buddha already in 500 BC, roughly speaking, said, is the soul immortal or not, or neither, or both? And you would think that if the two possibilities, is it mortal or immortal, that excludes everything else. No, he says, no, that's not true. Is it mortal, immortal, or not, or neither, or both? Then he says, no, there are many such statements. There are these famous contradictory statements in the canonical literature to this religion. Then he says, but I cannot give you the answer because I don't know the answer. Okay. And the Jains carried it further. They have 7 valued propositions in which a statement can be true, false, true but unknown to be true, very complicated things. So this is the fact is that for the mathematician, this is not an issue, either true or false. And there are reasons why it is, in most mathematical contexts, there is no problem with this. Now this ABM principle, I call it the ABM principle, never was accepted in India. They argued endlessly, under this context, under these circumstances, what will happen, this will happen, that will happen, and so on and so forth. But the practical resolution the Indian mathematicians found is, this is tricky subject, this is dangerous ground, we're not going to go there, we avoid it. So Indian mathematical texts do not have a single, to my knowledge, proof by contradiction, not one. And the person who is guilty of this extremely great loss to a mathematical technique is none other than our great religious leader, Gautama Buddha. But like all things in India, all thought process in India, I can trace it back. It has a prehistory. The prehistory goes back to the Veda, Rig Veda in particular. In poem 129 of Rig Veda, Book 10, Book 10 is the famous one of the late books. This poem is known as Nasadiya Sutra. It's well known because of the opening words in it. The state of the cosmos before the moment of creation. The uncreate in Stella Kramrich's superb turn of phrase is described as neither non-being nor being. The Nasadiya itself is dense with negations and double negations. In fact, it begins with a double negation. Na asat, appropriately, in the same book 10, poem 5 says, in case you haven't guessed, it's exact opposite, that the uncreate is both non-being and being. You can live with it, that's it. Now, many things in the more technical relationship between mathematics and others, literature, for example, poetry, which I haven't described because it requires time, it requires introduction of new ideas, and so on and so forth, and this is not the occasion for it. But there was never, as I said in my blurb, in India, everybody talked to everybody else. They would not always write down saying that, oh, I read Bhartrhari and I think he's wrong. That they won't say. But they would have known their Bhartrhari. They would have known their Panini. They would have had their heads stuffed with Panini when they were kids, when they were in their formative years. But if they don't use Panini's method, they must have had reservations. We don't know what they are. So it's a very, very fascinating field of work, I think. And I hope very much that lots of people will take to this. Thank you very much.
Thank you, Mr. Divakaran. We'd now open the floor to a few questions, if anybody has any.
Now, I'm quite happy to answer questions. I should have said this from the beginning.
Yeah.
What happened to me?
Is there anybody with a question?
Yeah.
That first picture with the picture with the square, the first one. You said your starting point is drawing that line and then picking the midpoint. How did they find that midpoint?
You had done it in school.
No, with a foot ruler. Did they have a foot ruler then? Or?
No. You don't need a foot ruler, I'll tell you.
Yeah.
Okay, I want to find O.
Yeah. Yeah.
You take your compass, put it on W, and draw that circle. This circle. With the radius equal to the full length.
Okay.
Okay? Then you do the same thing with this as the center, draw this circle, identical.
Yeah.
Then you have them hitting one another and end that with this line. Join them.
No, on the last bit, say that again, please. Last one, say that again.
This line, I know this point, I know this point, I join them, it cuts the EW line.
Ah, okay.
You've done it in school.
I'm sure, yeah. Okay.
You need a memory card.
Yes, this is true.
Yeah, that's how it's done. Now they. Yeah.
These aspects of the history of mathematics, are these casually referred to in institutions that teach mathematics? Has it ever been thought to be part of the curriculum, at least to give a background?
Now?
Yes, now.
That's a tricky question. I mean, question is not tricky. The answer will send it into trouble. My answer would be.
Why don't you say it anyway?
Sorry?
You said it might get you into trouble, but why don't you speak out?
No, I'll say what I want to say. There is a great, the history, the history of our intellectual past has been mishandled over a very long time by very many people, and it is still being mishandled badly. There are several phases to it. There are several stages we have gone through. In the beginning, the study of India's past, especially its intellectual past, began at the end of the 18th century. And the great moving force in that study was Sir William Jones in Calcutta. And because he was a linguist, he discovered many languages, including Sanskrit and other Sanskrit-derived languages, came to the conclusion that linguistic studies can be very scientifically conducted by doing things. At the same time, he encouraged some of his colleagues, one of them actually in the court in Calcutta, Henry Thomas Colebrook, to go back and look at astronomy texts. And there was one, Mr. Samuel Davis, who was also encouraged to do the same thing. And they were the first people to produce translations of authentic Indian texts. The first work translated was part of Bhaskaracharya's Lilavati, and part of great work by Brahmagupta called Brahmaspura Siddhanta. As a result, there was a tremendous awakening of the spirit of, and this spirit lasted till about 1830, 1840. And there were many, many names, not very famous names. For example, Charles Wyche, who collected manuscripts, translated them, wrote on them, gave lectures in the Royal Asiatic Society in London, and so on and so forth. However, something happened. People say it is the mutiny, the Great Rebellion. Something happened, and beginning in 1860 or 1870, the European approach, especially the British approach to Indian knowledge systems, became extremely narrow-minded, full of biases. There are many, many reasons for it. One of them was that it took till about the middle of the 19th century for the Europeans to discover their own intellectual heritage in classical Greece. That was a time when, suddenly everybody had to learn Euclid, Aristotle. Everybody had to read Aristotle. So, as a result, the Europeans came to the conclusion that, we have our roots, intellectual roots, in the Greek tradition, and the Greeks are Europeans, forgetting the fact that very substantial parts of Greek knowledge of mathematics and astronomy came from the Mesopotamians, who lived much before them. So that is the time when everything was attempted to be traced back to ancient Greece, classical Greece. So when the Indian mathematical texts came up, I said, I meant Shulba Sutra. I said 800 BC. Oh, they said, no, it can't be 800 BC because some of these things are in Euclid. This is a poor man's version of Euclid. And this is done by people who did not fully understand what is in Euclid. Oh, this is nonsense. It's not true. Okay. So it went through this phase. And that phase lasted a long time. And it still is alive. There are still people who write on these things, still saying that the Indian, many of them, some of them are extremely technical. They are derived and they are said by very, very great people. I mean, I was talking to one of my colleagues earlier today saying, a very great French mathematician called André Weil, who has written on history of mathematics, and in particular on the history of Indian mathematics. And he will say, without batting an eyelid, oh, this, according to so-and-so, a man called Paul Tannery, a French guy, was derived from Pythagoreans. Pythagoreans lived before Euclid. There is absolutely no ground for saying it. They had no idea what they were talking about. So there is this thing, and that continues. Even now, for example, there are well-known names in the history of mathematics, which I don't want to talk about, who got most of these things based more on their prejudices rather than objective evaluation of actual evidence. Now there is a reaction, as you would expect. Now we are very much more conscious of our own intellectual strengths, very much more conscious of our nationalism, of our patriotism. Now we say, what do we say? That not only did we invent calculus in India, the Roman Catholic priests came here and stole it from us, for which there is no proof, no evidence whatsoever. Okay. So, it's the usual tension. So, now there is, as far as schools are concerned, the people who think that Europeans stole calculus from India are now involved in rewriting textbooks, as you probably know. This national education policy that people talk about, it has many appendices. Appendices are, somebody has to produce the material for the kids to be fed. And I know several committees who do this work, and I would be afraid of what they're doing. I would be. So I've expressed my views clearly.
I'm really sorry, but we're all out of time. Yes. Thank you, Professor Divakaran. Thank you so much for being here. Thank you to all of you for spending this lovely evening with us and Professor Divakaran.